All right, section 3.9. This is the last section of chapter 3. It's all about energy diagrams. We're going to talk a lot about these throughout the semester. Notice we're introducing a lot of concepts. Mine's a little different than what the book is, not too much. But we'll talk a lot about this to understand why certain reactions occur, why do they occur, what's the reasoning, what's the driving force. Reactions just don't occur just because you want them to. All right, they obviously have to have a particular reason for them to occur. All right, and understanding, and it's all about energy. Everything in nature is about energy. All right, Einstein said E equals mc squared. So anything that has mass has energy. Energy has to be favorable. If it's not favorable, it's not going to want to do it. So let's take this reaction that we learned in 3.8 again, where the double bond grabs a hydrogen and kicks out your chlorine to form the carbocation intermediate. Okay, and this is, like I said, it's called an intermediate. All right, this process of this arrow attacking the hydrogen, all right, is called the transition state. Okay, this is a transition state. Why is it a transition state? It's because it's the state at which you're transitioning from your starting materials to your intermediate. So they call it T1. It's kind of a T with two crosses. So that's the transition state 1. This is our intermediate. When your chlorine now attacks your carbon, this is transition state, that's transition state 2, and you form your final product, CH3CH2Cl. Okay? So let's talk about the energy with this molecule, all right, and what this all means and why it's important. So this is an energy profile. The y-axis is energy, the x-axis is time. Okay? Now, your starting materials have a certain amount of stored energy in them. All right, so this is where your starting materials are. I'm going to draw small just so I can fit everything in here, plus HCl. So there's some sort of energy associated with the bonds and the electrons. Numbers, I'm not going to worry about numbers. We're not going to do any calculations. But there's a certain amount of energy that's stored inside of your molecule. Okay? When you start breaking and forming bonds, that requires energy. You need energy to start making and forming bonds. Okay, so the energy of these compounds start going up as you approach transition state 1. So while your pi bond is grabbing the hydrogen on the HCl, all right, there's a certain amount of energy associated with that highest point. Okay, that's your transition state 1. And it tips down to a plateau, all right? The energy associated with this plateau, all right, whatever energy it is, that is the energy in the intermediate. That's your intermediate. Okay? In this case, our intermediate is the carbocation. Okay? And it's usually higher in energy than your starting material because it's a charged compound. Then your chlorine attacks, and you have a second transition state. That's the highest peak of that reaction. And then eventually you form your products. The reaction comes down and forms whatever energy is in your product. Okay? All right, so you have transition state 1, transition state 2. That corresponds, the 1 is the double bond adding to the HCl. Transition state 2 is when the chlorine attacks your carbocation. All right, and this would be an energy profile of the reaction. It shows what energies everything is associated to. All right, obviously, not obviously, hold on, let me first define it, then we'll say obviously. This energy right here, the energy from your starting material to your transition state is called the activation energy, E sub A. E sub A is equal to activation energy. Activation energy. Okay. You also have one right here between your intermediate and your T sub 2. So that's activation energy 2. Let's call this one activation energy 1. All right. But the point is it's from some sort of lower plateau to a transition state. Okay. Now, your reaction, the speed of the reaction, the rate of the reaction is based on how big E sub A is. Right? If E sub A is so gigantic, your reaction needs a lot of energy for it to go. The reaction might not even go. It might not even have enough energy for it to go. Or it could be that the energy is pretty small and the reaction goes very, very fast. Okay, so it really all depends on what the size of the activation energy. Okay, your overall energy, the energy of the reaction, is the energy from the starting point to the energy of where your molecule has ended, or the energy of the products. So that is what's called your overall energy. You might have heard the word enthalpy. It's the enthalpy of reaction. All right, it's the overall energy. If your products are lower in energy than your starting material, this is an exothermic reaction. Exothermic means energy is released, and it means your products are less than your reactants as far as energy-wise. All right, an endothermic reaction is the exact opposite. Endothermic is energy is absorbed into the molecules. You need to add energy absorbed. All right, this is where your products are greater than your reactants. And that would look something like, let me just do a little mini thing here. It would look something like you would have whatever your activation energy is, and then your final product would be higher in energy than where you started. Okay, so that would be what an endothermic reaction would look like. Okay, but going back to this, the most important thing to understand is your intermediate, the energy of the intermediate. If you have low energy intermediates, if the energy of the intermediate is much lower, that means that reaction can happen much faster because it implies your transition states are lower. Okay, reactions are dependent on the energy of your intermediates. Also, the how much energy you need for the transition states. Okay, so once we start doing more reactions, we'll start doing more of these plots, but I want you to know the names of the areas, the activation energy, the intermediate energy, the transition states, the overall energy, or the enthalpy. Okay, now there are things that you can do to change the rate of the reaction. One of them is by adding a catalyst. Okay, what does a catalyst do? A catalyst changes the rate of a reaction, changes rate of reaction. Shorthand for reaction is RXN. I'll start doing that from now on. By lowering the activation energy by changing the mechanism. Now this part is something that you might have not have learned, by changing the mechanism. When you learn about catalysts in Gen Chem, you basically learn it lowers the activation energy. That's it. But you don't learn why or how it lowers the activation energy. But now we're going to go more into it. It's by changing the mechanism of the reaction. Okay, let's say we have a reaction. Okay, all right, I'm going to kind of exaggerate this. Let's say here is your activation energy. All right, and let's say in this case it's a one-step reaction. Okay, so here's starting materials, here's product. Okay, let's say it's a one-step reaction. All right, here's your transition state, here's T sub 1. All right, so my E sub A activation energy is right there. What a catalyst does, when you throw in a catalyst, the catalyst is now involved in the reaction. So it's no longer A plus B is reacting. It's not, so let's say this big reaction is A plus B gives me, let's say, Z. Okay? Well, when you throw a catalyst, what happens is A reacts with your catalyst to form some sort of AC, a catalyst compound. Then your AC then reacts with compound B and forms Z. Okay? Notice this reaction is different. Now there are two steps in the reaction. Okay? The first step is just A plus B gives me my product Z. Here, A has to react with C, and then AC then has to react with B to form Z. I'm changing the mechanism of this reaction. So by doing that, technically maybe these steps have lower activation energies. Okay, so here's T sub 1, T sub 2, Here's now intermediate. Now my activation energy of the catalyzed reaction, notice, is much smaller than the activation energy of the uncatalyzed. And not only is it lowering the activation energy, it lowers it by changing the mechanism. And that is the important part that I want you to get out of what a catalyst actually does. The other thing to note is that it doesn't matter if reaction is catalyzed or uncatalyzed. The energy of your starting material is and the energy of your products. So your overall energy, our enthalpy, which I think I forgot to mention, the way you show that is a delta H. Your delta H is the same. It's equal. Equal in catalyzed and uncatalyzed. Okay. Catalysts don't change the overall energy of the reaction. It just changes your activation energy. It changes how much energy you need in order to get to your transition states. All right? So that is it for Chapter 3. And that's it for Chapter 3.